Thanks for bearing with us, and welcome to our presentation, which is going to be given by myself, but also by Tom Wayman from Auto Aviation, about some interesting things we're doing as we speak in physics AI models with the hard data about the accuracy of these models and how they may actually impact some of the workflows that we're all involved in. So as a way of telling you a little bit about what I'm going to be discussing, we're going to start talking about the simulation landscape and how it's changed and how it needs to change, but more specifically, how physics AI models can impact that simulation landscape for many of the workflows that in aerospace we're interested in. I'll then make an announcement about a new foundational model that we're going to call Shift Wing, so I'll reserve some of the details for a little bit later on. And then finally, we'll go into some examples and some final parting thoughts. So let me actually begin with some general context setting for how engineering simulation needs to evolve. And what I have to say is that while engineering simulation has been incredible in helping us design way better products than was possible before, we have missed a number of key opportunities. And there are three, and they're pervasive in any industry, in aerospace in particular. But first has been the GPU revolution. If anybody doesn't think that the GPU computing revolution has arrived and GPUs are the fundamental way of doing simulation in the future, I think you need to sort of rethink about what you're doing at the moment. The second thing is the advent of the cloud, modern software engineering practices for handling very large amounts of data, and the APIs and SDKs that securely allow you to access computational resources, but also at the same time some very, very large compute capabilities. And last but not least, the topic of today's discussion, so physics AI itself. And what actually matters is that you don't have to look at each of these technologies separately, but rather when you look at them all together is when you start seeing some opportunities to change the way in which we do simulation-based analysis and design. So let me go in that direction. So many of you have heard about physics AI, physics-based AI, ML, physics-constrained models, et cetera, as a surrogate replacement for the high-fidelity simulation that we currently have. And of course, you've seen sort of flowcharts like the ones that you see over here, where the design loop that requires the repeated prediction of different variations of a design happens very, very quickly because the simulation engine has been replaced with this physics AI model. That is one paradigm of how this may go down in the future. But there are many other situations to enable the things that you see below, and in particular, some that are highlighted where you may rely on these physics AI models, but at the same time, you may also query the high fidelity model, the simulation that you see over there, in order to get adaptive type models that become better and better over time and actually give you the accuracy that you require in order to do the workflow that you need. So I'm going to talk about physics AI models in that context. Regardless of how you create the physics AI models or how you consume them, and whether you mix in high-fidelity simulation, what is very clear is that generating sufficient amounts of data in order to ensure that you have the accuracy that you require is absolutely the bottleneck. So something needs to be done in order to be able to generate all that data. Of course, in order to generate large amounts of data, first you have to generate a single simulation. And that's an entire path that is fraught with human intervention, with lack of automation, with many different failure points, starting with importing the geometry, to preparing that geometry for meshing, to simulating or setting up the simulations, and then actually running the simulations, and eventually making sense out of what comes out of the simulation. So obviously, in order to enable physics AI, you have to have the entire sort of beginning to end workflow, what we call the inner loop of the simulation. And it's absolutely critical. At Luminary, we've been working in every one of these elements, making them as fast and robust as possible and automating them so that you can actually have a hope and a prayer of generating large databases that then get consumed as physics AI models. So it's not only about those individual elements, but it's also about the platform that puts everything together such that you can manage not one, not 10, not 100 simulations, but thousands or tens of thousands of simulations, and that is tricky. So it starts with a full cloud-based infrastructure massive compute resources, massive storage, and then of course it layers on top a number of different things that eventually culminate on services that can be provided to the simulation consumer. In particular, APIs and SDKs that securely allow the access instantly from any time, from anywhere, anytime, to these massive amounts of data that you've actually created. So let me actually move forward and sort of make some quick definitions. So what do we mean by physics AI and what can it do for you? So by physics AI, we mean the application of advanced AI and ML, machine learning techniques that actually specifically tailor to respect physical laws, symmetries, and invariance. And of course, you may know this, but if you haven't heard before, the idea of bringing physics into the AI models has a certain number of benefits. So first of all, you could reduce the amount of data that is required to train a model of a given accuracy, right? If you keep the accuracy fixed, the physics AI models give you a chance to have higher accuracy in the model that consumes the same amount of data. But most importantly, the generalizability of the results, the prediction of designs that you have not seen in the training data is vastly improved by our ability to actually have sort of physics AI models. So as you know, whereas standard surrogate models have always been focused on scalar output quantities of interest and regression of those output quantities of interest, in physics AI, we're also inferring the surface and the volume fields. And there are a number of advantages that I'll mention later on that shortchange or take away some of the basic steps that are normally required in the simulation world. So at Luminary, we've gone through all of these different things, through large-scale data generation and automation, differentiable solvers, end-to-end workflows with APIs and SDKs that allow us to have a modern way of addressing large amounts of data, and of course, interfaces with lots of different third-party software that normally are required to do our work. So the objective of these models is to obtain the necessary accuracy and also the generalizability, and of course an understanding of whether the accuracy that a prediction is providing is sufficient or not. So last year I was looking through the New York Times and there was a great article that was titled "AI Can Write Poetry but It Struggles with Math," and the actual creator of the IBM Watson, so the early days of artificial intelligence, said that for a lot of things that really matter, sort of painful accuracy and precision is actually required. So this is typical in aerospace engineering, obviously. How do you go about generating physics AI models if you're not familiar with it? Well, it starts on the left-hand side with the generation of a typically large data set. Huge investment in actually computing variants of the design at different operating conditions, so on and so forth, and curating that data such that you start with a database. And of course, you pre-process that data to get it ready for training. And then once the data is ready, you actually run any of the available AI ML model architectures to train a model that can then be used for inference, and it can be used for any of the applications that you see there. At Luminary, we want to shortchange, or to, not sort of shortchange, but to rather shorten the actual path to go from the beginning to the end of having a physics AI model that your organization can consume. So we actually start with what we call shift models and databases that give you a large number of simulations for specific domains. And then we also provide you with a pre-trained model for those specific cases. With the addition of domain-specific or problem-specific data, you can retrain that model relatively quickly and both accelerate the time to get to a physics AI model, but also vastly improve the accuracy in the applications of interest. And of course, you know, in the inset there, you see that the next leap of engineering is going to be in putting all these things together, but also rethinking the engineering workflows to take advantage of these models that can now execute relatively quickly and can give you the accuracy that you need. So at Luminary, as I mentioned, we don't believe on the capability today of generating a foundational model for an entire broad set of physics, let's say fluid dynamics, but rather we're very interested in looking at specific domains where we can generate large data sets and models that can give you a leg up to start running physics AI models in your workflows. And while there are a number of the ones that we're pursuing today, I'm really happy to announce that we are launching, after this presentation, what we call Shift Wing. So it's a data set and the associated physics AI models that's been done in collaboration with Auto Aviation and with NVIDIA in order to facilitate high-speed wing design. So let me talk about this shift wing model that we're announcing today. Let me actually just sort of give you a rough idea of how it works. So obviously we've generated a whole bunch of data sets. You see some samples of those particular data sets. It's going to be the largest open source and the highest quality data set. I'll go into depth into that in a moment. The most comprehensive data set available for transonic wing design. So we're releasing it today with 3,000 simulations. They're all RAND simulations, but they're using what we call LMA, so highly adapted meshes in order to get the accuracy that is actually needed. And the data set will be available for non-commercial use in Hugging Face. So we are continuing to add simulations as we speak and enhancing the parameterization in order to arrive at a predictive capability in the moment and lift and drag coefficients that gets close to 1%. And that is also in the surface shear stress and pressure distributions that I'll show you. We think this is a starting point for people to add their own simulations in their designs in order to get to specific design problem answers that you might be interested in. If you're curious, go to luminarycloud.com/models. So we started with a NASA CRM. Let me talk about the parameterization and the geometry. We got a whole bunch of macro parameters for the parameterization, and then we're adding micro parameters at a number of different airfoil sections, fuselage, wing body fairing as well, and then of course running a sample of any one of those parameters through a solution that is quite detailed about adapted mesh refinement Y+1, 30 million cells, which gives you the equivalent resolution of about 150 million cells when you're not doing adaptation. And we've run it through lots and lots of different calculations. So of course it produces beautiful pictures like these ones. You'll see the weight gets animated because the resolution is extremely high. And if you want to see some of the meshes, you actually will be able to access them directly in Hugging Face to understand the accuracy of the database that we're relying on. So if you want to look at the types of variations that happen, both in geometry on top and in the solution on the bottom, this is just an animated loop of many of the samples, not comprehensive at all, of what the model is actually seeing and the information that it's drawing upon in order to sort of fit the particular model. So substantial variations in geometry, lift coefficient, Mach numbers, so on and so forth. In fact, the distribution of force and moment coefficients is quite large. So on the top line, this is the distribution for lift coefficient, drag coefficient, and moment coefficient at Mach 0.5. And the bottom line, you actually see the same quantities and their distributions center about the logical locations for Mach 0.85. So we'll be dealing with a subsonic case and with a supersonic case. If you want to see it in slightly different ways, lift versus drag, CL square over pi aspect ratio over drag for Mach 0.5, every dot in these plots is a separate, highly adapted simulation, and the distributions are the ones you see with the marginal distributions on the side. So this is for Mach 0.85, where compressibility drag actually plays a much bigger role, and the linearity that you saw before in the Mach 0.5 plot is a little bit different. So the data set includes very reasonable wings and very unreasonable wings because we want to teach the model the ability to predict things that are in the neighborhood of an optimal design, but also far away from it, and to do so accurately. So if you look at 3 sections, inboard, midspan, and outboard for the Mach 0.5 sort of samples, you see pressure coefficient variations like the ones that you see here. And if you go to Mach 0.85, you see many flows with different shock waves, et cetera, et cetera. So this is kind of the distribution of the data set and the solution. I have not told you anything yet about the model, but that is what the model relies on in order to do the predictions that I'm going to show you in a moment. So let's talk about inference accuracy. So I'm going to focus on measures of accuracy that look at the lift, the drag, and the moment coefficient. And we created effectively a cost function J that weighs the errors evenly for those 3 coefficients based on the baseline from the drag prediction work. So roughly, the errors that you'll be seeing that I'll be talking about are going to be the joint errors of these 3 different coefficients of interest. So let's think about the distribution of the test sets, so things that we have not put into the model, but we try to assess the accuracy of. you're going to have a distribution of that error. And of course, the best prediction errors, so the leftmost side of the graph, give us, with about 2,000 simulations, I ignored to say that so far, although this is going to be increasing as you'll see, lift coefficient errors of about 1.65%, drag coefficient errors of 0.17%, so slightly over a count, and moment coefficient errors that are really quite small. Of course, you could say, what is the absolute worst prediction that this model can actually come up with? And for this amount of data, the absolute worst prediction has errors between 3, 5, so on so percent. The median predictions that you see with the purple line are actually showing you what's reasonably expected from about 1,000 to 2,000 simulations in these particular models. So errors that are small, but not small enough yet until we add more data. So, of course, the average drag coefficient, you can look at other things. The good news is that as we add data to the model, we retrain the model and we assess the errors. And we can build an extrapolation to understand what size data set is going to be required in order to get those force and moment coefficients below the 1% accuracy target that we're setting for shift wing. And the answer is somewhere between 10 and 20,000 simulations. And that's what we're marching towards in order to get there. I gave you the bad news first. This is Mach 0.85. Shock waves, discontinuities, extremely hard to predict. So if I animate this slide, these are the results of Mach 0.5, where the solutions are far smoother. And of course, as you can see, the mean prediction errors are now almost within the 1%, even for the small data set that we have. But for transonic conditions, additional data is going to be needed. How does it work? Well, look, for example, at Mach 0.85, let's look at the best possible prediction, top view of the pressure coefficient distribution on the wing. Of course, we're randomly perturbing all these variables. So the twist variables are changing, and you see that shock location that is actually not quite straight. But this is training data that is valuable for the model to actually learn. If you click next, that is the actual prediction that takes about 2.5 seconds of the surface CP prediction for that model in the best case scenario, right? So you can see with the I norm is not very different. If you look at the actual pressure distributions for this transonic case, you can see that there's slight mispredictions in the locations of the shock, but it's actually predicting the locations of the shock quite well. And overall, for something that will take about a couple seconds to execute, it's really not bad. But it is a surrogate model that carries some error and gives you the ability to almost near instantaneous analysis compared to the full CFD simulation. The interesting thing is that same case, the best case for skin friction coefficient predictions, top view, is actually quite a complicated flow with separation in the wing body sort of intersection, some post-shock separation, et cetera, et cetera. The prediction from the model is remarkably close as well. I have a whole bunch of different cases for Mach 8.5, but for Mach 0.5, et cetera, et cetera. I'll show you a couple others. In the spirit of full disclosure, you're engineers. You care about accuracy. You want to use a model when it's accurate enough. This is the absolute worst prediction from the model at Mach 0.85. So you can see that it has shock waves, expansion, so on and so forth. If you look at the prediction of the model, again, full CFD solution on the left versus actual, physics AI model, what you can see is that there's, it's not identical, but it's relatively close. When you look at the actual pressure distributions, you can see the inboard section is well captured. The mid-span section or half-span is reasonable. And then there's some actually differences in the location of the shock in the tip section. You can also look at the prediction and the CFD calculation for the skin friction coefficient in the worst case scenario. And you can look at the median case. This is what you should expect from these models with about 1,000 to 2,000 simulations. When we get to 20,000, you should expect a lot better than this. So median test case, CP distribution. That's the typical sort of distribution of pressure that you see, or coefficient of pressure. That's the actual prediction from the AI model on the right-hand side. And then, of course, reasonable sort of accuracy in the predictions themselves. At Mach 0.5, there's not much to see. Things are much smoother, more linear, simpler, so everything works better, as you saw in the hard data. So, you cannot see much difference there. This is the best case scenario for Mach 0.5 samples. The pressures are nailed. And remember, these are cases that we did not use in training. If you look at a median case, You can see in the color maps, you actually don't see anything that you could see, but you actually see that it's pretty accurate with some slight differences in various different places. So let me just invite Tom Wayman to tell you a little bit about auto aviation, but also the way in which we collaborated in order to put together the parameterization for this particular model. And then I'll come back to try to sort of recap and sort of give you some final thoughts. So Tom, would you like to take over, please?
We got a mic. There we go. All right. Well, thanks again. My name's Tom Wayman. I am the Technical Fellow for Applied Aerodynamics at Auto Aviation. And for those of you who are not aware of what we do or what we're planning on doing is we're planning on fielding a business jet. And so this is our opportunity to kind of discuss that with you. This is called the Phantom Business Jet. And we believe what we have here is a phenomenal design, one that is really on the verge of shepherding into this generation, a new efficient business jet. So how are we going to go about doing this? We firmly believe that where we're at with this is a radical reduction in the energy required for flight and design of this new transonic business jet and this class completely. It's our intent to bring this to the small and mid business class market and do this at a super mid jet performance by leaning into the laminar flow technology that Auto Aviation brings to the table. We're going to be accomplishing this through what we call the virtuous cycle. We're in significant reductions in drag. We get significant reductions in fuel burn. We get significant reductions in the amount of payload that we have to carry for fuel. We have significant reductions in the amount of both propulsion and structural components, and which eventually leads to reductions in both the maintenance, the production, and the operation of the aircraft. It's our intent to put this aircraft together with the capability with 3,500 nautical mile range, with flight conditions around 51,000 feet. Now, this isn't an easy task. I think, as most of you know, I think as undergraduates, probably in engineering, you were introduced to boundary layer theory, and you said, okay, there's three types. There's laminar, there's transitional, and then there's turbulent. And as an undergrad myself and a budding new applied aerodynamicist, I was really fascinated with the airfoil sections that showed a lot of laminar flow to it. But all that technology that was in those airfoil sections was always with a caveat that it couldn't be produced, it couldn't be manufactured, and it couldn't be maintained. And so it was kind of one of those kind of letdowns that you were thrown this thing in front of you that had great potential and great efficiency, but you couldn't implement it. It was a bit of a holy grail, a bit like a single stage to orbit or like a boomless supersonic flight. So for Auto, though, our quest really is to basically obtain laminar flow across the majority of the primary lifting surfaces. Our challenge, though, it permeates the entire culture. It's not only within engineering, but within manufacturing and operations as well. And so what we're bringing forward for this is the opportunity to basically promote a configuration that has laminar flow into not only the design phase, but into the production phase and the operational phase. And the largest part of that is ensuring that we have robustness in our concept, in our design. So a lot of our focus goes into a lot of simulation effort and designing that into it. It goes not only into our manufacturing methods, but also into the operation. Now, the key to this is our tools and our methods. It comes right down to how we use, how we develop, and how we validate our tools. And really, these are the primary challenges that Auto's facing with introducing this next generation. And it's the reason why we're partnering with Luminary Cloud to make this possible, not only for our engineers, but for our eventual customers of this product. And so the potential for us in physics-based AI really comes in the fact that we believe that the future of the aircraft design lies in the intersection between these first principles and the artificial intelligence. What we're kind of describing here essentially is a potential scale of physics-based simulations that can unlock the effort for Luminary Cloud that they have done, at least with the start for the Swift Wing. The potential enhancement in the throughput alone is enormous for my team in flight sciences, but the potential, if you couple that with optimization, there exists really an exceptional opportunity for us for real-time, real speed aerodynamic analysis. So the potential for us is acceleration in what we do daily and eventually when we get to our eventual products. Juan?
Well, thank you. Thanks, Tom. Thank you, Tom. So just to recap one more minute, the intent is to have models that are accurate enough such that you can query them many, many times. So obviously you could use this in conceptual design, rapid generation of load databases, actuator controls and surface control, surface sizing, even multidisciplinary interactions, but of course anything that involves uncertainty quantification needs to query many times. In order to make sense of all the data, this is an ecosystem, thousands and thousands of simulations cannot be looked at one at a time. So we've been partnering with our colleagues at TechPlot with their product Chorus in order to look at how to investigate all these data sets and in order to make sure that we can manage them, clean outliers, so on and so forth, prepare for physics, AI, et cetera, et cetera. And you see a little bit of an animation going on in the shift-wing data set sort of being operated on by Chorus. And to wrap up, the last 2 years have seen tremendous and very rapid progress in the applicability to engineering and aerospace engineering workflows of physics AI models. So data availability through GPU computing, advanced physics AI architectures, but also modern SDKs and cloud-based platforms in order to orchestrate everything. So we do see the possibility of getting to 1% accuracy in these models relatively quickly in domains in which the data is actually generated for. And we're proud to announce this shift-wing model and the associated data set in order for people to begin experimenting. So please come by the booth.